Good morning. This is Joe Morosco again, and this is part 2 of a 3-part series on making better decisions and handling uncertainty. In this part, we're going to answer the 3 big questions that always come up once you've laid the foundation for Bayes. Where we left off at the end of part 1 was a series of 7 statements or 7 sentences that describe the Bayesian update process, which is shown at the right. And our conclusion was that this is very, very similar or identical to what we call the scientific method. And what Bayes has provided us is some apparatus that allows us to calculate how our probability estimates can be updated when we get new information. There are 3 frequently asked questions. In fact, it's unusual to do this presentation and not have all 3 of them asked. So we're going to do them one by one. We're going to do the first one in this part, and then we're going to do numbers 2 and 3 in the 3rd part in this series. So the questions come down to this. What's the formula? People have numbers and they want to know what to plug the numbers into to get other numbers which represent answers. So we're now going to go back and fill in that step we skipped in part 1, and we're going to actually show you the formula and where it comes from. And then we're going to move on to part 3, and we're going to address the question of how the new information gets weighted. We've talked an awful lot about weighting the new information, and we're going to flesh that out at the beginning of part 3. And then we're going to finish with something that troubles a lot of people. How do you figure out what that prior probability is to get started? And that turns out to be a lot less troubling than it first appears. So in order to get the Bayes updating formula, we're going to use medical diagnostic testing as an example. And we have a good reason for doing that. Medical testing or medical diagnostic testing is something that almost everyone has come in contact with. And what we're trying to do when we administer a diagnostic test is to improve our estimate of the probability that the person has a disease. And we're going to administer what we call a admittedly imperfect diagnostic test. We're going to get to that in a minute. And the test is going to come back positive. And that then leads to the question, what is the updated probability that the person has disease? Because we have new information. The person tested positive. That's information we didn't have before. So it's a question now of how much has the probability increased due to the positive test result, or we could also ask the question, how much does the probability decrease if the test came back with a negative result? Here's where we make the point that all tests are imperfect. And once again, most people understand the notion that sometimes tests come back with the wrong answer. And these are called false positives and false negatives. And what we've done here is create a table which is made up of historical data with this test. And what we see is that with 100 uses of this test, the test got it right 85 times, and that's shown here in the green squares, where the person had the disease and tested positive, or did not have the disease and tested negative. So 85 times out of 100, this was a good test. On the other hand, there are false positives and false negatives that we have to deal with. And that's shown here, where a healthy person tested positive, that's not right, or a diseased person tested negative, that's also not right. And what Bayes does is use this table to numerically evaluate the strength of the test. And that's based on how many false positives and false negatives we get. So this table is very, very important. I'll also take this opportunity to emphasize excuse me, that the no test is perfect rule applies everywhere. It's not just medical testing. Anytime we get new information, that information needs to be viewed with some skepticism and needs to be, considered in the light of, well, it might be wrong. And so for every test that we do, whether it's a medical test or not, we have these 4 possibilities, and we need to consider the test in light of those possibilities. So, what's our approach now? Well, traditionally, what happens at this point is people start explaining conditional probability and introducing some new notation to express that. And my experience with that approach is that it's almost universally a failure. And the reason is that you have to stop and start explaining conditional probability and explaining the new notation. And that's a distraction. So we're going to dispense with all of that. And what our approach is going to be is to do it all with words that everybody can understand, and to not introduce new concepts at this point. So here's what we're going to do. We're going to compute the probability that the patient has the disease and tests positive for the disease. And we're going to examine that question from 2 different points of view. The point of view of the disease and the point of view of the test. Now, both of these different points of view reflect the same underlying reality. So whatever answer we get from the disease perspective, we ought to get the same answer from the test perspective. And we're going to use that fact to demonstrate or derive, if you will, the Bayesian update formula. So starting from the disease perspective, we have 2 conditions that must be satisfied. First, the patient must have the disease, and we're going to indicate that by this notation, probability has disease. Secondly, the test has to come back positive if the patient has the disease. And we're going to indicate that probability by probability tests positive if has disease. Okay? Now, for both those things to be true, the combined probability, or the AND, we need to take the product of those 2 probabilities, this one and this one. So we multiply those 2 probabilities to get the AND. And we're going to draw 2 blue boxes to link the probability from the perspective of the disease point of view down here in this blue box. Now, let's view what it looks like from the test perspective. First, the person has to test positive, and we indicate that here, probability tests positive. And then the patient must have the disease if the test comes back positive. And we indicate that by probability has disease if tests positive. And once again, using the same logic, the combined probability, the AND, is just the product of those two probabilities. So here's our multiplication sign, and here are the two probabilities that have to be multiplied together. We'll put a red box around that. Okay, so we've analyzed this now from two different perspectives. But they're the same. Both represent the combined probability of having the disease and testing positive. So the red box must equal the blue box. And there it is. There's the red box and the blue box, and all we've done is put an equals sign between the two of them. Let's remove the red box and the blue box, and we now have an equation with two terms on each side of the equals sign. Okay, so we have a total of 4 terms. And now let's solve for the unknown that we're really looking for, which is the probability that the person has the disease if they test positive. And we can do that by the simple matter of dividing both sides of the equation by the probability to test positive, and that will isolate the term in the oval. So now we have this thing in this blue box which says that if we know these 3 quantities, this one, and this one, we can get our answer with 1 multiplication and 1 division. Simple arithmetic. And you know, that seems pretty simple, and we don't need any complicated notation. We just need English, and we now have a formula. So there's a reward for getting that formula, and that is we're going to actually plug numbers into the formula and show how we get an answer. So now we get to the arithmetic part. So the first thing we want to concern ourselves with is this term here, the probability of having the disease. And if we don't know anything before we do any testing, we can look at column 3 of our table. And what that tells us is that historically, if we test 100 people, 30 will have the disease, 70 won't. So the probability that the person has the disease is just 30 over 100, or 0.3. So that's our prior probability, which is probability that it has the disease. Next, we need to look at what the probability is that the person tests positive if they have the disease. That's this term here. And to do that, we just look at row 1. Okay, so of all the people that are diseased, 30 of them, 25 will test positive and 5 will test negative. So this term here, which is shown here, is 25 out of 30. Okay, that's the probability that we'll test positive if we have the disease. And lastly, we need the probability that we test positive. And we can get that from row 3, okay? Out of 100 people, 35 test positive, 65 test negative. So that probability is just 35 out of 100. And we see that here, 35 out of 100. Okay? So we have 3 terms, this one, and this one. And we now have numbers for all 3 of those. And if we clear all the fractions and, just do the arithmetic, this comes out to 25 out of 35, which is 5 out of 7, which expressed as a decimal number is 0.714. So we have an answer. Testing positive raised the probability from 0.3, which was the prior, to 0.714. So testing positive raised the probability. In fact, it more than doubled it. It went from 0.3, which is less than 50-50, to 0.714, which is, definitely more towards the true side. And the other crucial observation here is that if we had a weaker test, if we had larger numbers in these red cells here, that would have been a weaker test, okay, because it got the answer wrong more times than this test. The result of having tested positive would still be an increase in the probability. It just wouldn't have gone up as high as 0.714. So what we see here is that this table actually tells us the strength of the test. Okay, because we use this table to get the numbers that we plug into the formula, which ultimately gets us to this answer. So that's our reward for having derived the formula. The table and the formula together gets us the answer. Now, what about negative test results? Well, of course, tests don't always come back positive. Tests can come back negative. And the question is, when a test comes back negative, how much will that decrease the probability that the statement is true? And we have an analogous equation to our baby blue box. I'll call it the baby pink box. And this is the formula that you use when the test comes back negative. So there's actually 2 formulas. And you need to use the one that's appropriate, depending on whether the test comes back positive or negative. So now I want to talk about what I call the big picture. And we're going to put all of the information we had on one slide. So here's our prior probability of 0.3 and our positive test result probability and of 0.714, and we also computed using the pink box formula the negative test result probability, which is 0.077. And now let's put this on a graph. So here we have the prior probability, which starts out at 0.3. And if we get a positive test result, we come up to 0.714. And if we get a negative test result, we come back down to 0.077. And if we had a perfect test, which we know we'll never have, the probabilities would have gone up to 1 and gone down to 0. So what we're seeing here is that the effects of the positive test result and negative test result, because of the false positives and false negatives, we get to 0.714 instead of 1.0, and we get to 0.077 instead of 0. So this illustrates graphically the effects of having a test which is not perfect. Now there's a couple of other things we could look at. The test is asymmetric, and by that we mean when we had a positive test result, we increased from 0.3 to 0.714, so we went up to 0.414. On the other hand, when we had a negative test result, we went down from 0.3 down to 0.077, a decrease of 0.223. So notice that the positive test result increased much more than the negative test result decreased. And that is a reflection of the fact that we had different numbers in the false positive box and in the false negative box. Now, this is a really important slide because this encapsulates pretty much what Bayes is all about, and how even though we have a test that is imperfect, in other words, it doesn't remove all of our uncertainty, what the Bayes formulation tells us is how can we still use this information, okay? We have imperfect information, but what we can do is put a number on where we came from and where we are now. So it's a quantitative procedure which lets us use the new information and weight it. So this is all about this weighting idea, okay? If you're having problems understanding this, I would stop the presentation at this point and go back a few slides and work your way through it, because if you understand this slide, then you understand Bayes. Okay, I'd like you to take a deep breath. This is the end of part 2, and we've come a long way. We have derived 2 equations, or 2 formula, that allow us to do the Bayesian update. And we've seen how the imperfection in the test leads to weighting the new information and coming up with a new prediction. And even though the test is imperfect, we still get very useful information about the updated probability. We'll stop here and we'll conclude in part 3. I hope to see you soon.